Here we go. We're going to take 72.86 grams of sodium thiosulfate. By the way, is anyone in photography at all? Has ever developed your own film? Let's put it that way. Has anyone developed their own film? We've had this conversation last year. Okay, this sodium thiosulfate. And Jonah's the only one. He's already had the conversation, so I'm not going to go any further. Doesn't matter. Seriously, he's the only one that's going to get it. So, boom, 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 boom. Let's find out.
So, doesn't the sodium cause the cyanotype? Isn't that for like
Say this again?
The sodium causes the cyanotype for blueprints. Isn't that where that comes
That
from?
I don't know.
Okay. So it's a
The
different.
what?
When printing for photographs, there was some mixture that had sodium in it for cyanotype, which is like the blueprints,
Oh, really?
which is where that
Didn't
came
know
from.
that.
And I wasn't sure if that was what you're.
No. I was
Okay.
actually referring to the fact that this is the stuff that fixes
that's
the
the
silver
mixer.
ions
Okay.
onto the paper fixer.
Yeah, that's the same fixer.
The second tray. And the third tray is water. Yeah, moving on. So, given 72.86 grams of sodium thiosulfate, how many sodium ions are present? That's an interesting question, isn't it? So what do we need to do? Now that we've been through really nearly everything we need to know for this stuff, you guys tell me what to do. Anybody can shout this out. Jama, don't be shy. Oh, we're not sure where to start. Well, we're going to need Avogadro's number at some point in time. Okay, here's what I suggest. Chemistry, at least in your world this year, is like 85% about the mole. Last year was almost all about the mole, right? This year decreases a little bit. We got other things that are going to be going on too, okay? But it's all about the mole. So I would highly suggest converting to moles. So go ahead and convert this to moles. You know how to do that. But don't come up with an answer. Just do the setup for converting to moles. Don't come up with an answer yet. Of course, everyone knows that the atomic mass of sodium is 22.99, very good. And everyone knows that the atomic mass of sulfur is 32.06. Everybody knows that the atomic mass of oxygen is 16. You did know that one.
15.9.
No, 16, because 100th place. 100th place.
Yep.
In fact, periodic tables, the AP periodic tables, if I remember correctly, only go out to about the 100th place. So they've already done all that work for you. Does anyone have an average atomic mass yet? Or molar mass yet? They want to shout out.
0.4608 moles.
Yeah, I know. I was looking for the
Oh,
the molar
total
mass.
mass 158.1.
Anyone agree, concur, 158.10? All right. Now, and again, I said don't come up with the answer yet. Because here's where I think you guys are like, well, here's the question. It's a little bit like stoichiometry. How many sodium ions are there in, how many moles of sodium ions are there in 1 mole of sodium thiosulfate? There's 2 moles, right? There's 2 sodiums, wouldn't you agree? So there's 2 moles. So this is like a little bit like stoichiometry. So, whoa, thought that was the flask. So there's 2 moles of sodium ions for every 1 mole of the sodium thiosulfate. Would you guys agree? And that's the little trick to this problem. Okay? And now we just convert those moles to particles using Avogadro's number. So basically, we just multiply whatever answer we had gotten from our standard mole thing, multiply it by 2 because of the 2 ions. We'll go ions here. Now, just for fun, don't touch your calculators there. Yeah, I know. And I'll let everyone catch up. But let's see if we can kind of come up with a possible, oh, this is easy. Oh my gosh. Jeez. Wow. Okay. Let me see, who am I going to pick on? Somebody else. Alicia. It was kind of funny when I was saying, who am I coming? I saw so many heads start going like this. Alicia. Just estimating, if you haven't touched your calculator yet, right? Other than to do the molar mass. What's the answer to one significant figure? Nobody else touched your calculator? Would you guys all agree with that? Yeah, that's what I said. That's pretty darn easy, isn't it? We cut it in half, then we multiplied by 2, didn't we? Okay. So we should be around 6 times 10 to the 23rd. Did anyone actually do it yet? 5.55. 5.55. That's pretty darn close to 6. Wouldn't you agree? Just by doing it in your head. And we need another significant figure.
550.
Really?
Yeah.
Wow. Okay. Boom. There we go. That's pretty easy, right? There's not much more I'm going to do with that right now. Let's go on to something better. Are you guys okay? Well, shoot. Should I do it or not? Are you guys okay with percent composition by mass? Should I just review it really quickly?
Was that the last question on the quiz?
Oh gosh, no. No. Here's the issue that you were having, and it wasn't just you, there were like 3 others that were having on that last question. I need an X, where do I put it? Was that the question that was going through some of your heads? I know there's an X in here somewhere, I'm not sure where to put it. Here's where I'm going to explain that to you. How many of you are doing X, Y?
That's what I did.
Yeah, that would work if you remembered how to solve an equation with 2 variables, which is not all that hard, but there's an easier way. When there's only 2 percentages, the best way to do that would be assign one of them X and the other one 1 minus X. And now you're going, right? That's good, because now you know for the next time. What did you try to do? You did X and Y? Is that what you did too?
Yeah.
Okay. What did you do? Did you do that? Or did you go X? Or did you go X minus 1? Some people may have done that. Doesn't matter. It's a long time ago. Well, for you it was. Awake time. You're kind of sleepy right now, aren't you?
Yeah, I drank a cup of coffee this morning.
Just one?
It was like a big cup of coffee.
Okay. I drink like a pot, so.
Well, I don't usually drink coffee.
Oh, okay. Moving on.
That was the question.
Next, percent composition by mass. If you recall, and I'm just doing this really quickly because we already have half the information. Remember, the molar mass of this was 158.10? Okay. So if it's 158.10 grams per mole, that's the total. Obviously, the percent is always a fraction of the total. So what we have to do is find the mass of the sodium individually, find the mass of the sulfur, find the mass of the oxygen, divide by a total, convert it to a percent. Boom, boom, boom. Okay? So we're going to do 2 sodiums. We're going to do 2 sulfurs. And 3 oxygens. You guys know your multiples of 16 really well, right?
32.
Where's the?
Hi, Mr. Borzak. Physics is here. Somebody?
Yeah. Somebody welcome. Just at some point, I want Casey to try to explain to you what happens when someone jumps off the building with emotionally heavy boots.
Oh, dang it.
With what?
No.
What?
Remember, there was a physics discussion in English class today.
Emotionally
Emotionally heavy boots.
boots. So I heard you correctly.
Right? Am I correct?
Yeah.
Emotionally heavy boots. So we'll discuss that later.
Okay, and so we add all this up, it came out to 158.10. So we would divide each one of these things by 158.10, multiply it by 100, and we have our percent. Okay. Boom, done, over. You guys were really, really good at that. A couple of you may have forgotten what that was. So we reviewed it really quickly. Does anyone have any questions? Now, where another piece of this this is an application of that, and it's like a little shortcut. You don't actually have to do all this work necessarily. I may give you a problem where, what was the mass of sodium thiosulfate that I had given in the previous question? 72 point something? 86, okay. So we could actually do this. I could give you a question where you're given 72.86. And I know we're bored with this substance and these numbers, but the point is, why do more work currently than we have to? I can get the same amount of work done here. And let's say I want to know what mass of thiosulfate ion is present in this. So this is similar to the how many sodium ions question, except now we're looking for the mass of the thiosulfate piece. Well, if you think about this, it's kind of very closely related to this percent thing. If we knew the percent of sulfur and oxygen, because that's what thiosulfate is, right? And then, this is obviously not 158.10, so the mass of the thiosulfate is going to be something less than the sum of these two things to some extent. So if I knew what that percent was, okay, I could multiply that percent by this. But that would require you to do all this stuff. Okay? There's a faster way. Somewhat faster way. We're going to go ahead and take this, and then all we have to do is look at the relationship between the mass of the components of thiosulfate, sulfur and oxygen, okay, which turns out to be what? 112.12? You guys do that math real quick in your head? Correct me if I'm wrong. And occasionally I am. So, but I'm getting 112.12 there for these. Okay? And then just divide that by the total. That represents the percent of thiosulfate in the total. Because that's the math you would do to find that percent. Would you agree? So you don't even have to go do the whole thing. You can just use that relationship. And there's our mass of thiosulfate. Just for fun, what would that be without touching our calculators? I think you can get it to almost two significant figures here. Not quite, but pretty darn close. Definitely one, almost two. I'm probably a little less than 56. 56 would be half, right? 73 divided by 158, a little less than half. So what, 53 or so? Does that make any sense? You can check it anyway, do it. So you guys are, you guys are going to be good at that. 51.67? Okay. Okay, and there's that. And this is all stuff you guys I believe every one of you was exposed to this in regular chemistry at one point in time. Again, for some of you it was 2 years ago, others of you it was a year ago, and that's enough too. Do you agree? We forget it, but pretty easy stuff. All right, next, empirical molecular formulas. So this is kind of what I just got done doing, was applications of mole mass conversions and percent composition. Empirical and molecular formulas. Does anyone remember the difference between an empirical formula and a molecular formula?
Empirical formula is the smallest ratio of whole numbers.
Ratio, the whole smallest whole number ratio of the elements in a compound, and whereas a molecular formula is the true formula, or the actual number of each element. A couple really good examples of that work out pretty well. I always like to start off with this, which we all know as glucose. That is the molecular formula for glucose. If you were to have a molecule of glucose, it would have specifically a ratio of 6 carbon atoms to 12 hydrogens and 6 oxygens. Everybody's clear on that, everybody gets that. What is glucose's empirical formula? Yeah, CH2O, which is the lowest ratio possible. Now, sometimes that empirical formula actually exists as a separate, as a real thing. And this would be an example of that. You do not have to know this, okay? I'm just showing you that CH2O actually does exist. Don't worry about that, don't write it down. It's formaldehyde. That's the formula for formaldehyde. It's the simplest aldehyde there is, okay? However, there are many times when it doesn't exist. So for example, does anyone recall what that is? Hydrogen peroxide. That's the molecular formula for hydrogen peroxide. In order to exist as hydrogen peroxide, you have 2 hydrogens, 1 oxygen. What would its empirical formula be? HO. That does not exist. Now, some of you are sitting here thinking, well, wait a minute, what about OH, which is hydroxide? But remember, that's the hydroxide ion that has an extra electron associated with the system, which is not that. Okay, so that doesn't exist. Now, interestingly enough, some students kind of wonder about this one a little bit. Does anyone happen to know what that is? Somebody whispered it. That is sucrose, table sugar, stuff poured over cornflakes this morning. Is that the empirical or molecular formula? It is a molecular formula. And also the empirical formula, because you can't reduce that any further. Right? So that one happens to be both. So we're clear on the distinction between the two. Okay. There's some labs, there's some techniques, I should say, that you can use to determine an empirical formula. In fact, some of the labs that we're going to do this year, we're actually going to go through the process of figuring out what the formula of we're going to know some tools that will allow us to figure out the formula of an unknown substance. We'll do some things, we're going to be able to figure out the empirical formula. Well, actually, there's some things we can do to find out what species are in the substance. First of all, identifying what elements are there, or ions, whatever it happens to be. Then we can figure out the empirical formula. There's some techniques we can learn that will help us figure out the empirical formula. Does anyone remember how, if you know the empirical formula, we get to the molecular formula? There's another piece of information we need. That'd be the molar mass, okay? And there's going to be some lab techniques in which we're going to learn how to determine the molar mass of an unknown substance without even knowing what it is, okay? So when you put all those things together, now you've got this substance, you have absolutely no idea what it is. You can do some laboratory techniques to help not only identify it, but find out what its formula is, which is kind of cool. Or you can go buy a $1.5 million machine called a mass spectrometer and figure that out too. But we don't have one of those handy here. As nice, I don't know if you guys many of you will find this out when you go to college and actually go into a chemistry lab. We have a pretty nice facility for chemistry here already. I mean, this is wonderful. The equipment is wonderful. Some of you will find this out depending on where you end up going to school that, oh, I wish I was back in high school because we had better stuff. Okay? Now, that's at the undergraduate level. Now, you start working your way up, yeah, that's going to go away. Like I said, that mass spectrometer thing. But, yeah, so isn't that cool? We already have this really nice facility, and they're building us, theoretically, a better one. We'll see how that goes. I may elect to stay here. I actually don't want to leave. I like this room. Ouch. Sorry about that. Maybe I better put this away. You guys don't keep a random ring stand near you? Next, how do we go from the empirical formula to the molecular formula? I'm just going to grab a handy-dandy question from our old book, just for fun, because these are hard to make up off the top of your head. You really screw them up if you do. Oh, this is awesome. Right here, let's do this one. So, let's say we have a substance. You guys ever heard of styrene? No, apparently not. That's no fun. We're not going to do that one. No. Let's do a different one. Ibuprofen. I like ibuprofen. Do you guys like ibuprofen? Let's do ibuprofen. Okay, so here we go. So we're going to go 75.69% carbon, 8.80% hydrogen, and 15.51% oxygen. This is determining an empirical formula. Now remember, as I believe it was Noah that had said earlier, empirical formula is the lowest ratio of the moles of elements to each other in a compound. Okay? You're going to be provided with two different types of information. You might be given percent composition data or percent composition by mass information. That might be provided for you. You may just be given actual masses. Either way, it doesn't matter. Does anyone recall how to handle if you're given percents? It's okay if you don't. Okay, so what you do if you're given percents is you assume 100 grams of compound. Because if you have 100 grams of the compound, then each of these percentages becomes masses, right? So there we go. So we've got 75.69 grams of carbon, we have 8.80 grams of hydrogen, and we have 15.51 grams of oxygen. And as I said earlier, empirical formulas is the lowest ratio of the number of moles of each element relative to each other. What do you think we're going to do with those grams? Convert to moles. Okay? So we're going to convert to moles. You guys can do that really quickly. I'll trust you. There's a certain period of time in regular chemistry where we spend a lot of time doing one technique. Convert to moles, divide by the smallest. Convert to moles, divide by the smallest. You guys may remember hearing that phrase before. Convert to moles, divide by the smallest. Who's got calculators out that they're using? I see Colin has one. Colin, could you do the carbon? Could you do the hydrogen? And somebody do the oxygen. Who's going to do the oxygen? You got the oxygen? Okay, good. All right. Colin, shout it out when you get the answer. And if anybody tell me what element that you're doing and you have an answer for hydrogen. What do you have?
8.73.
8.73. Go one more just for fun.
Oh wait, that's actually 8.71.
1.3. Excellent. 1.3 moles. Okay.
Oxygen 0.9694.
4 moles. And
Me?
yep.
6.302.
Okay. And like I've already hinted at this. Once you've got the moles, what do? Divide by the smallest. Well, you can either do that as it stands. Some people like to do it this way. Gosh, I hope this turns out to be what I wanted to do. And so what do we get? Well, obviously the oxygen's 1.
You multiply all this on top.
No. What I'm doing, I cheated. Each one of these will be divided by that.
Oh.
So instead of doing it, writing this out 3 times, I just did it that way. And we'll have the carbon.
6.50.
Ooh, good. I was hoping that would happen. Carbon is 6.50 something. Yeah, okay, that's close enough. Hydrogen,
8.99.
excellent, 8.99. Okay, so now we have a scenario where we have the ratio of the moles of elements to each other. Actually, we had that earlier with the 6.302, the 8.713, and 0.9694. But none of us recognize that as any formula that we would ever use or know what it is, right? So then we divide by the smallest, okay, to try and put them in relationship to each other. Well, now we've got 1 oxygen, essentially 9 hydrogens, would you agree? But we've got 6.5 carbons. What are we going to do with that? No, we're not going to round it up. It's too far away. We're going to multiply by the entire thing by 2 to get rid of the half. See where I'm going? 0.5 represents 1/2, so we get rid of the 1/2. We're going to multiply by the reciprocal, which is 2. So we're going to multiply the entire darn thing by 2, so we get C13H18O2. Is that still an empirical formula?
Yes.
Absolutely. You can't reduce it any further than that. I'm glad that doesn't happen all the time. Usually, not usually, often after this step, you get whole numbers. Now notice, that's not technically a whole number, right? But when we're doing these calculations, you have to remember this comes from experimental data. There's going to be some error involved. You've done enough experiments to understand that there's error involved. And even if you did it perfectly, that whole estimation piece on the measurements, that has some error in it. So there's always going to be some error. Anyway, however, occasionally you run into a scenario where you don't come up with a whole number on one of the items here, and so you're going to have to manipulate the data a little bit to get those whole numbers. Some common things you might run into. What if we came up with 6.32? What's the 0.32 represent approximately? 1/3, so you multiply by 3. What if you ended up with something like 4.21? What's the 0.21? Really close to 0.5, you multiply everything by 5. See how that works out? That will happen on occasion. For example, the 8.99, 8.97, something like that, because of the experimental error, you can round those up. Okay? Pretty good. Oh, I see you guys packing up. I'm looking at this thinking I've got 2 more minutes, so I'm going to keep going. So the next step is, here's the empirical formula. What if I wanted to know the molecular formula? Well, one way or the other, whether it's through another experiment or someone else had done the experiment already and provided this information for you, what if the molar mass had been 206 grams per mole? So in a different experiment, the molar mass had been determined to be approximately 206 grams per mole. I say approximately because depending on the substance, some of the techniques to come up with that, it's only valid to like maybe the 10th place or even the 1's place. So anyway, 206 grams per mole. Well, what you would do is find out what the empirical formula mass is. So right off the top of my head, I'm thinking 120, 64, 90, that's right around 200. I don't know if anyone's done it already. Okay, it's right around, trust me on this one, it's right around 200 grams, okay? So if the empirical formula mass is 200-ish grams, and the molecular formula is 200-ish grams. This is not only the empirical formula, but it's also the molecular formula. You divide the empirical formula mass into the molecular formula mass. Because if you remember, the molecular formula is a multiple of the empirical formula. We just have to find out what that multiple is.
It's 206.3.
Is it really? Yeah, so. Hey!
Number from the book.
The 206 point, yes.
Oh, so
Yes,
I guess
that was provided.
I guess that was the,
Turned out to be
molecular
exactly the same.
formula.
Right. All right, so anyway, you guys start working on that assignment. It's due Friday. We're going to be doing other things, including at least one lab.
It is Friday.
Yeah, you got a week.
See you at 11.
See you. Good luck.
Good job.
Good luck. Staying awake.
Yeah, because I could go listen to opera talk for 50 minutes.
Well, you did pretty well with mine. There, we just covered 3 days of regular chemistry in 45 minutes.